Okay, so for part two for refraction at a spherical surface, we take a look at three examples. The third example will eventually lead us on into lenses. Okay, the first of the three examples, however, is concerned with the paperweight example, taking a look, for example, at the image of the scuba diver that is here in the paperweight. Go ahead and access today's lecture examples and copy down the first problem. Okay, so that first problem is as follows. It says, find the image for the following situation where the object distance is 5 centimeters and the radius of curvature is 10 centimeters. Okay, so right here is that situation. Here's the optical axis. This right here is the glass. This is where light is going to start. Think of the object itself, the scuba diver, for example, as a light bulb. So that's the easiest way to picture the situation. So the light is coming from the object itself in that sense. Okay, right over here is the air, like so. So you're basically holding the paperweight like this and you're looking through it in that direction. Okay, and then right here is the scuba diver. We'll just draw the object here as a point. That's perfectly fine for this topic. Once again, this right here is the object O. So we're given that right here is the object distance DO. The object distance is given to us as 5 centimeters. It's a positive number because the object is on the same side of the surface from where the light is coming from. Think of the light as coming from the object itself. So DO here is a positive number. That's positive 5 centimeters. Okay, and then the center of the sphere is over here. The radius of curvature is 10 centimeters. So if this right here is 5 centimeters, here's another 5 centimeters like so. Right back here is the center of the sphere C like this. This distance here is the radius of curvature. However, the center of the sphere is on the same side of the surface from where the light is coming from. Therefore, we have to make the radius of curvature a negative number for that reason. So the radius of curvature is negative 10 centimeters. Okay, now the hard part is over. In other words, we've identified everything. We've used the sign convention correctly. The last thing to do is just plug everything into the expression and then just solve for the image distance. Once we do solve for the image distance, then we can draw the situation. All right, so let's go ahead and plug in. So I have 1.5 over positive 5 plus then 1 over di equals then 1 minus 1.5 and then divided by the radius of curvature, which remember is negative 10 centimeters. And now all that we do here is we just solve for di. So let me go ahead and do the math. So let's see, on the right-hand side, we have 1 minus 1.5, which is negative 0.5. The negative signs cancel, like so. And now I'll go ahead and I'll just do the math here on my calculator and then solve for di. So the right-hand side is 0.5 divided by 10, and then subtract 1.5 over 5. And then lastly, I take the reciprocal now to get di by itself. And what I do, I end up with the image distance di as being equal to negative 4 centimeters. So the image then forms 4 centimeters from the surface itself, but the negative sign means that the image forms on the same side of the surface from where the light is coming from. So then therefore, if this right here is 5 centimeters, 4 centimeters is about right here. So then therefore you see the image of the scuba diver here a little bit closer to you within the glass than it actually is. Now that we know what the answer is, now we can draw the situation. What I'm going to do is just take 2 light rays coming from the object. I'm going to refract them across the surface. When I do, the refractions look like they're coming from this point. Now the first refraction to draw is just one along the optical axis itself like so. We always draw this light ray here for this situation. And then just arbitrarily a second light ray, say, from the object to this point here. And then when it refracts as if it came from this point. Therefore, the easiest way to draw this very simply is to just do this, like so. Notice that this light ray here and this light ray here are diverging from each other. So then therefore, if these 2 light rays here entered your eye, they would then look like they're coming from this point. That's then where the image forms. So basically, the answer tells you how this has to look. Okay, let's go ahead and move on now to a nice application in question number 2 of today's lecture's examples. This has to do with looking at the bottom of a swimming pool. How many of you have ever noticed that if you're standing on the side of a pool and you look down at the floor of the pool appears shallower than it actually is? It's actually explained by this topic, refraction of a spherical surface. Okay, so let me go ahead and erase here. Once again, copy down now example number 2 from the lecture examples. Okay, and then for this example, right here is going to be the surface of the water. It's perfectly flat. This then means that the radius of curvature will be infinite. And then right here is my optical axis, like so. Okay, right here is where the light is going to start in the water with that index of refraction, and then the light is going to refract into the air. And then think of this point right here as a point at the bottom of the swimming pool. It's like a light bulb at the bottom of the swimming pool. This right here is our object. Right here is the object distance. The object distance is the depth of the pool, 10 feet. Okay, once again, however, it's a positive number because the object is on the same side of the surface from where the light is coming from. And then, as I indicated earlier, the radius of curvature is equal to infinity, because if you have a perfectly flat surface, then the sphere is extremely large. It's infinitely large, in fact, if the surface is a plane. And now that we've identified everything, we just plug everything into the expression. So usually the hard part is just identifying everything and getting the sign convention correct. After that, the situation is easy. So I have right here 1.33 over 10, and then plus 1 over di equals then 1 minus 1.33, but then the denominator is equal to infinity anyway. And then therefore the right-hand side of the expression is equal to 0. And now I just solve for di. So I'll do the math. We have here 0, and then minus 1.33 over 10, so negative 1.33 over 10. And then lastly, I take the reciprocal here to get the image distance di, and this ends up being about 7.5 feet. So di is equal to negative 7.5 feet. So once again, the negative sign here for the image distance means that the image forms on the same side of the surface from where the light is coming from. So if this right here is 10 feet, 7.5 feet is about right here, like so. So then therefore, if you were over here somewhere and you were looking down into the pool and you were looking at this light bulb, you would then see its image as being a little bit closer to you than it actually is, so the pool appears shallower for that reason. Okay, now that we know where the image is, then we can go ahead and draw the situation, and drawing the situation here is much like the last example. So light ray from the object like so, just going along the optical axis. We always draw this light ray here. Okay, and then just arbitrarily a second light ray like so. And then when this light ray refracts from the water to the air, it refracts as if it came from here. So once again, the easiest way to draw that is to just simply do this, like so. And then these two light rays here and here are diverging from each other, so then therefore if they entered your eye, they would appear to be coming from this location back here. Okay? Okay, and then we get to the most important example for this lecture, and that's the third example. In this third example, now we're going to begin to think of the paperweight as a lens. So what we're going to be doing is we're going to be looking through two surfaces, and then therefore we're looking at something else in the room. So now what I'm doing is I'm looking all the way through the paperweight at objects on the other side of the room. I'm beginning to think of the paperweight now as a lens. So then therefore I'm going to have to refract the light twice because I have here two surfaces. Incidentally, by the way, this is a really lousy lens. Okay, let me go ahead and do some erasing here. As I'm doing, go ahead and copy down problem number 3. Okay, so I'm going to draw this nice and large. I suggest you do the same. Okay, the paperweight, it's made out of glass, so it has an index of refraction of 1.5. is 20 centimeters thick, and it has 2 radii of curvature, each equal to 30 centimeters. An object is 10 centimeters away from the paperweight, and you look all the way through the paperweight. Where does the final image form? Okay, okay, I'm going to give myself some room here. Let me go ahead and draw the paperweight like this. Like so. Here's my optical axis. And then we're sitting over here, looking all the way through the paperweight in an object that is over here. Okay, now this index of refraction for error is 1. This is glass, 1.5. And this is back to error once again. Okay, it says that the paperweight here has a thickness. The thickness is usually referred to as small t. In this case, it's given to us as 20 centimeters. There we go. Okay, and then we have here 2 surfaces, each with the same radius of curvature of 30 centimeters. There's going to be a surface here, R1 we'll call it, and a surface here, R2. We'll call it, each one is 30 centimeters. Now, for now, I'm just writing down the number 30 centimeters, but I'm going to use the sign convention to get my positive signs and negative signs correctly in just a few moments. Okay, and then we have our object just 10 centimeters away from the paperweight. So right here is the object like so. Right here is the object distance. The object distance here is given to us as DO, and it's equal to positive 10 centimeters. The reason why it's a positive number, once again, is because the object itself, think of it as a light bulb, for example, is on the same side of this first surface here as where the light is coming from. And now what we do is we do the first refraction. What I'm going to calculate is the image distance for the first refraction, and then we'll use that image distance to get the object distance correctly for the second refraction. So we break this up into 2 parts. Okay, so for the first refraction, now let's go ahead and get the radius of curvature here, R1, correct with its sign convention. The center of this sphere is over here somewhere. It's on the opposite side of the surface from where light is coming from. Therefore, from the sign convention, it's a positive number. Okay, now I'm just going to go ahead and plug everything into this refraction expression, and what I'm going to solve for is the image distance for this first surface. I'm going to give it a name. I'm going to call it di prime. So what I have right here is the following. 1 over the first object distance of 10 centimeters, plus then 1.5 over the image distance called di prime, equals then 1.5 minus 1 divided by the radius of curvature R1, which is positive 30 centimeters. Like so. And now what I solve for here is this first image distance di prime. So I'm going to do all the math for us here on my calculator. So what I'm going to do is 1.5 minus 1 divided by 30, so 1/2 divided by 30. Subtract from that 1/10. Okay, now I'm going to go ahead and take the reciprocal and then multiply by 1.5 to get the image distance di prime by itself. And when I do this process, I end up here with negative 18 centimeters. So the first image forms 18 centimeters away from the first surface, but the negative sign means that the image forms on the same side of the surface from where the light is coming from. So then therefore, on the top coordinate looks like this. So right here, if this was 10 centimeters, then maybe about like right here is 18 centimeters, like so. So right there is the image for the first surface. And now that we know where that image is, now I can start to refract 2 light rays. When I refract 2 light rays coming from the object across this surface, they will then look like they're coming from here. So then therefore, the first light ray just goes like this. Okay, and then just arbitrarily a second light ray, like so. And then when I refract it across this surface, it looks like it comes from here. I'm going to draw it like this. Watch this. Like so. If you take these two light rays here and extend them back, they look like they're coming from here, like so. And now here's the key to the problem. How do we do the refraction here across the second surface? Where is the object for the second surface? Well, take a look at these two light rays that hit the second surface. They look like they're coming from here. So then therefore the image for the first surface now has to be thought of as the object for the second surface. So what is the object distance now for the second surface? That's this distance right here. Notice that it's equal to 18 centimeters plus the 20 centimeter thickness of the paperweight for a total of 38 centimeters. It's a positive number. The reason why is because this object here is on the same side of this surface from where light is coming from. Here's then how we write this mathematically. Okay, the object distance for the second surface, I'm going to give it a name. I'm going to call it DO prime. This is equal to the following. Notice how this is written. This is negative of negative 18 centimeters for positive 18 centimeters plus 20 for a total of positive 38 centimeters. Like so. Once again, this is the key to doing the problem. Okay, and then we've got the radius of curvature here, R2. Once again, it's equal to 30 centimeters, but now watch this. The center of this sphere is over here. It's on the same side of this surface from where light is coming from. Therefore, it has to be written as a negative number for that reason. So this right here is a negative 30 centimeters, like so. Okay, now that I've got everything identified, now I'll once again plug everything into the expression and we'll solve for the final image distance. The final image distance I'm just going to refer to as DI. So here's then what the equation looks like. I have 1.5 over 38 plus then 1 for air over DI equals then 1 minus 1.5 over negative 30. So, and now I just solve for DI. Okay, once again, I'll do the math for us. So the right-hand side is 1 minus 1.5, so that's negative 0.5, and then divided by negative 30, negative signs cancel. So 0.5 over 30. Okay, and then I subtract 1.5 over 38, and then I just take the reciprocal. So when I do, the final image distance DI ends up being negative 44 centimeters. So the final image forms 44 centimeters from the surface, that is the second surface, this guy here. But the negative sign means that that final image is on the same side of the surface from where the light is coming from. So I have to go 44 centimeters in this direction. Now this right here, remember, was 38 centimeters, so 44 centimeters is about back there. So once again, there's the image for the first surface, which was the object for the second surface. And then about right here, this distance here is 44 centimeters. This right here is the final image. So when I refract these two light rays now across this surface, they refract as if they look like they're come from back here. So this guy here just goes straight through again, like so. And now what do I do with that top light ray? Well, what I have to do is I have to bend it a little bit. I have to bend it a little bit in this direction such that when it does refract across this surface, it looks like it comes from here. So then therefore I basically have to do something like this. Like so. Notice how I kind of bent that down a little bit in this direction. And then if you take these two light rays here and extend them back behind the paperweight like so, boom, they look like they come from here. These light rays here would then be entering your eye. So this last example here is particularly important because next time it will lead us into lenses. That concludes today's lectures. Today's shirt was Merciful Fit.